All right, let's just jump right into it. Welcome to This Explainer. Today, we're going to completely dismantle one of the most famous science cliches you probably learned back in high school. You know the one, right? The rubber sheet, the heavy weight in the middle, the rolling marbles. Well, our goal today is to totally shatter that flawed analogy and help you build a true intuitive understanding of Albert Einstein's general theory of relativity. Because honestly, reality is far more mysterious and way more fascinating than a bowling ball sitting on a trampoline. To kick things off, I want to share a quote I found from a Reddit user named Offseason that just perfectly captures the glaring problem with how we usually teach this stuff. They wrote, "It's always bugged me that to rephrase gravity from a magical action at a distance into something purely geometric, the common illustration still needs just as magic a force. It is such a brilliant Socratic observation. We're constantly told that the trampoline represents Einstein's version of gravity, but it secretly relies on an outside force pulling that heavy ball downward, doesn't it?" To really understand why this is such a massive issue, we need to look at the two absolute titans of gravity. For centuries, Isaac Newton's view ruled supreme. Newton saw gravity as this invisible force acting at a distance. And hey, it was highly successful. It predicted the motion of planets and projectiles perfectly for everyday life. But then Einstein comes along and totally flips the script. His radical new view was that gravity isn't a force at all. It's literally the curvature of spacetime itself, caused by the mere presence of mass and energy. But this reveals a super fascinating logical loop. Think about it for a second. If gravity is just the bending of space, what exactly is pulling the bowling ball down on the trampoline to create that bend? The answer is Earth's good old-fashioned Newtonian gravity. The analogy completely falls apart because it relies on the old Newtonian force to explain Einstein's new geometric gravity. It's kind of like using a horse to explain how a car engine works. It just doesn't make sense. Let's take it a step further. Why does a marble orbit that bowling ball on the trampoline? Well, the marble rolls down the slope because it experiences a normal force from the fabric itself, plus acceleration from Earth's gravity. It's just a classic physics problem of slopes and friction. But here is the absolutely crucial point. True general relativity involves zero physical forces and zero acceleration. None. An object in free fall in space is experiencing no forces whatsoever. It is simply, naturally, traveling along the shortest possible path available to it. And this is a brilliant way to illustrate what a shortest path, or a geodesic if we're being technical, actually looks like on a curved surface. Picture two people standing on the Earth's equator, maybe a few miles apart. If they both walk perfectly straight north, just following their noses, their paths start off completely parallel, but eventually they're going to bump into each other right at the North Pole. Now, if they didn't know the Earth was a curved sphere, they might assume some mysterious, invisible force pulled them together. That is exactly how gravity works. It's a total illusion created by geometry. So, how do we fix this broken trampoline model? Okay, first, we have to mentally turn off Earth's downward gravity. Just remove it. Second, instead of a heavy ball pushing down, imagine using a support underneath the fabric to bend it upward. And third, we've got to stop using rolling marbles. Instead, take a piece of flat, straight tape and try to lay it smoothly across that upward bump. That straight tape will inevitably wrinkle and curve to navigate the surface. And that bent tape, that represents the true, completely force-free path through curved space. But as great as that corrected model is, we immediately run into another massive roadblock. Seriously, think about this question. How do objects fall when they aren't even moving? If you just hold a ball in the air and let go, it drops straight down. It didn't have any horizontal path to be deflected, right? The whole fabric model only shows two dimensions of space, and it completely ignores the single most important dimension of all, time. This brings us to the absolute core of Einstein's genius. He realized you just cannot separate space and time. They are forever intertwined into this one unified thing we call space-time. And here is the mind-bending reality I really want you to take away from this explainer. Even when you are sitting completely still in your chair right now, you are hurtling forward through time. Because you are constantly moving through the time dimension, the curvature of spacetime can act on you, even when you are totally at rest in space. It is absolutely wild when you really stop to think about it. Imagine mapping this out visually. Picture three balls at the top of a cliff. One is dropped straight down, the other two are thrown horizontally at different speeds. Now, in regular 3D space, the thrown balls start facing the exact same direction, but their paths quickly diverge because the faster one travels further horizontally. If gravity was just bent space, they'd follow the exact same spatial track. But on a spacetime diagram, where time is essentially the vertical axis, these balls are traveling in completely different directions right from the start, simply because they are moving through time and space at different rates. So the absolutely crucial point here is this. Almost all the everyday gravity you experience, dropping your keys, being stuck to the floor, is due to the warping of time, not the warping of space. When you toss a ball across the room, it moves maybe a few meters in space, but it moves an enormous distance in time. To put that into perspective, in physics units, 1 single second is equivalent to about 300,000 kilometers. Because its journey through time is so incredibly vast, even a microscopic amount of spacetime curvature produces the visible, everyday arc of a falling ball. Now, physicists describe all of this curvature using Einstein's equation, G alpha beta equals T alpha beta. It looks deceptively simple, doesn't it? But actually, those tiny symbols are intimidating 4x4 matrices packed with incredibly complex tensor calculus. It's enough to make anyone's head spin. But hey, don't worry, don't click away just yet. We are definitely not going to do tensor calculus today. Thankfully, physicist John C. Baz figured out a way to translate that terrifying equation into plain English. It's brilliant. He wrote, given a small ball of freely falling test particles initially at rest with respect to each other, the rate at which it begins to shrink is proportional to its volume times the energy density at the center of the ball, plus the pressure in the x direction, plus the pressure in the y direction, plus the pressure in the z direction. Let's actually break down Bias's translation, because it's a game changer. If you have a cluster of tiny floating particles in a vacuum, the rate at which that cluster shrinks together is caused by two things. First, energy density. In everyday terms, that's just mass, like a planet. We all know mass attracts things, right? But consider the second factor in his translation: pressure in the x, y, and z directions. Einstein's math reveals the completely shocking truth that pressure itself also creates gravitational attraction. And this concept brilliantly illustrates what we call tidal forces. Imagine dropping a perfect sphere made of loose coffee grains. As they fall toward Earth, the grains closest to the ground accelerate just a tiny bit faster, stretching the ball vertically. But because they are all aiming for the exact center of the Earth, the ball also squashes horizontally. In a total vacuum, the overall volume of this coffee grain ball stays exactly the same. It just changes shape. That stretching and squashing, that is spacetime curvature in action. And it's the exact same micromechanic that causes our moon to pull the Earth's massive oceans into high and low tides. It's amazing how perfectly this stuff scales up. Speaking of scaling up, we can take Boz's shrinking ball of particles and apply it to the size of the entire cosmos. If you imagine the universe as a giant, homogeneous ball of particles, which is essentially what galaxies are when you zoom way, way out, Einstein's geometry becomes the literal blueprint for the Big Bang. Instead of a shrinking ball, we just have an expanding one. It's like the same mechanism, just running in reverse. When we map out the potential trajectories of our entire universe, we see that it behaves almost exactly like a Newtonian ball thrown straight up into the air. If you throw a ball up, it will either eventually fall back down, or if you throw it hard enough to hit escape velocity, it'll travel outward forever. Our universe is exactly the same. Depending entirely on its energy density, it will either eventually recollapse in a big crunch, or it'll just keep expanding forever in an open universe. But modern observations really threw a wrench into this whole elegant idea. We discovered the universe isn't just expanding, that expansion is actually accelerating. It's speeding up. To make the math work, physicists had to bring back something Einstein originally proposed and then famously discarded: the cosmological constant. This represents vacuum energy in empty space. And remember how we just learned that pressure causes gravity? Well, vacuum energy acts as a negative pressure, pushing the universe apart faster and faster. And honestly, even if we imagined a perfectly static universe, one that isn't expanding or contracting at all, the sheer geometry of space still rules everything. If you take a tiny ball of test particles and move it across a positively curved three-dimensional space, the inherent geometry of that space forces the ball to shrink in the transverse directions. It proves once and for all that gravity isn't some invisible tether connecting objects. It is an omnipresent, inescapable feature of curved spatial geometry itself. Which leaves us with one final, pretty provocative question to chew on. If it took humanity centuries to finally realize that gravity wasn't some invisible magical tether, but rather the very shape of reality and time itself, what other invisible forces in our lives, whether in science or even just in our daily perceptions, are actually just illusions born from our limited perspective? The geometry of the universe is vast, it's weird, and it's deeply beautiful. Thank you so much for joining me on this explainer, and remember to keep questioning the reality around you.